Algebra 2. Today we are going to take some notes on quadratic functions and doing the function family review. Okay, the parent function of a quadratic function is f of x equals x squared. This function creates a U-shaped curve called a parabola. The axis of symmetry is a vertical line that divides the parabola into two equal parts. The turning point of your parabola is called the vertex. The input-output table of your parent function looks like this. And looks like this on the graph. This point right here is your vertex, and the imaginary line that goes up through the center, your x equals 0 in this case, is called your axis of symmetry, or your AOS. All right, the standard form of a quadratic function is ax squared plus bx plus c. You find the axis of symmetry by using the equation x equals negative b over 2 times your a value. Then, to find the y value of your vertex, you plug your x value back into the equation to find the y value of your vertex. All right, here's an example. We have y equals 1, x squared minus 4x plus 1. Using our negative b over 2 times a, we have negative 4 over 2 times 1. That gives me x equals 4 divided by 2, which is 2. So my axis of symmetry, my AOS, is x equals 2. So I'm going to put that in the center of my chart here. When I plug these numbers back into my equation, I get these y values. When we plot these points on our graph, it looks like so. There's my vertex. 1 is negative 2. 0 is 1. And again, it is a smooth curve at your vertex there. Another form of the quadratic equation is the vertex form, and it is ax plus h, x minus h, squared plus k. Your axis of symmetry is going to be x equals whatever your h value is, and your vertex is your h and k. Here we have an example that is in vertex form. So the vertex taken from this equation is negative 1, 6. That should go in the center of your input-output table. And then we're going to build our input-output table from our vertex points. And then we'll graph based on these points. There is my vertex, negative 1, 6, negative 2, here and here. Those 2 points are mirrored. And then negative 3, negative 2. Here and here. And again, it is a curved line through the vertex. Turn the page. All right, so we're not going to do all of these. I'm just going to do a couple of examples. This is the only linear example we're going to do. If you want to go online and look at the answer key on our Google Classroom and look at the answer key, there is another example of a linear one on there, but I'm not going to go over that one. So let's just take a look at number 1. This is a linear function. The parent function is f of x equals x. It's linear because it's x to the first power. Remember from Algebra 1, this one is in y equals mx plus b. B is my y-intercept. And m is our rise over our run or our slope. All right, so my y-intercept is 5. So I'm going to go to 5 on my y-axis. 1, 2, 3, 4, 5, and put a point right there. Then my slope is negative 3 over 1. So I'm going to go down 3 and over 1. So my next point will be here. Down 3 and over 1. Down 3 and over 1. Down 3 and over 1. I could also go up 3, but I have to go back 1. Okay? This should form a straight line. All linear equations form a straight line. The domain of this linear equation is all real numbers. We're going to use all of our x values. The range is also going to be all real numbers. We're going to use all of our y values. The number of roots that a linear equation has is 1. It is going to cross the x-axis 1 time. The end behavior as x is going to positive infinity. My y's in this linear equation is going to negative infinity. As x is going to negative infinity in this direction, my y's are going up in this particular linear equation, so it is going to positive infinity. Our increasing interval is not applicable, and our decreasing interval, because it's a negative slope, is going from negative infinity to positive infinity. All right, let's take a look at number 2. This is an absolute value equation. And its parent function looks like this. Let's draw this one. This absolute value equation is in vertex form. We can pull the vertex right from our equation. And the vertex of this particular absolute value problem is going to be 1, negative 4. We don't need to do a t-table when we do absolute value problems because we look at our a value, which is right here, and that is also our slope. Okay, so let's plot the point, let's plot the vertex, 1, negative 4, which is here. And my a is 1 over 1, so it's going to be up 1 over 1, up 1 over 1 in both directions. Remember, our absolute value problems always look like a V. The domain of our absolute value problems are going to be all real numbers. The range depends on where your vertex is. My vertex is at 1, -4, so my range is going to be y is greater than or equal to -4. The number of roots that an absolute value problem can have is 2, meaning it's going to cross the x-axis in 2 possible spots. My end behavior of this particular absolute value problem, as x is approaching positive infinity, my y's are approaching positive infinity. And as x is approaching negative infinity, my y's are still approaching positive infinity. Increasing and decreasing intervals. It is increasing, it is going uphill, it has a positive slope, starting at 1 to positive infinity. It has a decreasing interval, it is going downhill, it has a negative slope from negative infinity to 1. When we're talking increasing intervals and decreasing intervals, we're talking about x values. Okay? So that's why this is a 1 here instead of a y value of -4. All right, let's take a look at number 3 then. Number 3 is a quadratic. And its parent function is f of x equals x squared. This particular quadratic is not in vertex form, so we need to use the x equals -b over 2 times a in order to find the vertex. My a value is -1. My b value is 8. And my c value is -11. So from here, we do -8 over 2 times -1, which is -8 divided by -2, which is 4. So the x value of my vertex is going to be -4. I'm sorry, +4. I find the y value of my vertex by plugging 4 in to my equation. So y equals -4 squared plus 8 times 4 minus 11. And when I do that in my calculator, I find my y value of my vertex to be 5. Now using a t-table, I'm going to find the other values that I need to graph this function. When I plug these values in, I get 3 is 4, 2 is 1, 5 is also 4, and 6 is 1. So let's graph this quadratic. 4, 5. 3, 4. That point is mirrored over there. And then 2, 1. And that point is also mirrored right there. So my graph looks like so. All right, let's talk about the domain and range of this particular quadratic. The domain of this quadratic is all real numbers. The range depends on the y value of our vertex. Our y value of our vertex is 5. So my range is going to be y is less than or equal to 5 because it's opening down. The number of possible roots that we have here is 2. It can cross the x-axis 2 times. End behavior. As my x is approaching positive infinity, my y's are going down to negative infinity. And as my x is approaching negative infinity, my y's are still going down to negative infinity. All right, let's talk about increasing intervals and decreasing intervals. Okay, increasing intervals and decreasing intervals. Again, we're talking about x values. So where is my parabola going uphill. Where is my parabola going downhill? It is increasing from negative infinity until this x value right here, negative infinity to the x value of our vertex, which is 4. Decreasing interval, where it's going downhill, it starts here and it goes to positive infinity. So it starts at 4 and it goes to positive infinity. Again, we're talking about x values, not y values. Okay? We'll discuss this more tomorrow. All right, let's look at 2 more. Let's look at number 7. So turn the page. And this is a parabola, a quadratic, but it is in vertex form. So again, this is a quadratic. And the parent function is f of x equals x squared. But this particular parabola is in vertex form. So it's giving us the vertex. Our vertex is 5, 6. So now let's use a t-table to figure out the rest of our values, starting with 5 in the middle, 4, 3, and 6, and 7. When we plug in those values, we get 4, 5, and 3, 2, 6, 5, and 7, 2. Let's graph this parabola. So like 5, 6. And 4, 5. Mirrored over there at 6, 5. And then 3, 2. Okay, graphing our parabola with a smooth curve. Now let's talk about the domain and range. The domain of this quadratic is all real numbers, as it is every time. The range of this quadratic is y is going to be less than or equal to the y value of your vertex. The y value of your vertex is 6. The number of roots that this quadratic can have is 2. Now let's talk about end behavior. As x is going to positive infinity, my y's are going down to negative infinity. As x is going to negative infinity, my y's are going down to negative infinity. Let's talk about our increasing intervals and decreasing intervals. My parabola is increasing from negative infinity to my x value of my vertex, which is 5. My parabola is decreasing from my vertex value, 5, to positive infinity. All right, let's do one more. Let's look at number 8. This is an absolute value problem given to us in vertex form. So absolute value. The parent function is f of x equals absolute value of x. The domain. Well, let's not do that till after we graph. Okay, so our vertex, because it's given to us in vertex form, our vertex is negative 3, 3. So let's plot that point. Negative 3, 3, which is right here. Okay, so our a value in our absolute value, our a is 1/2. Remember, our a value, when we're talking about absolute values, is also our slope from our vertex. So our slope, we're going from our vertex, we're going to go rise 1, or in this, yes, we're going to rise 1, and we're going to run 2. So up 1, over 2. Up 1, over 2, and so on. Now remember, this creates a V, so instead of going up 1, instead of going down 1 and back 2, we're going to go up 1 and back 2 to create our V here. Looks like so. All right, our domain of all absolute values is always all real numbers. Our range is going to be y is greater than or equal to, because it's opening up, the y value of our vertex, which is 3. The number of possible roots in an absolute value, again, is 2. Our end behavior as x is approaching positive infinity. Our y values are going up to positive infinity. As x is approaching negative infinity, our y values are going up to positive infinity. Okay, our increasing interval. We are increasing from this x value to positive infinity. This x value right here is negative 3. So negative 3 to positive infinity. Our decreasing interval, we are decreasing from negative infinity to this x value. So from negative infinity to the x value, negative 3. Okay? So there we go. You should now get your Unit 3 review, and your assignment is to do the odd problems.